Caveat. So the solicitation is it's on the street right now, and so we don't receive proposals till November, and consequently we don't have an awardee yet. So our plans are sparse. So if there's a lack of details in terms of the facility timeline, it's because of that. But I think what I can do today, and I think it'll be of interest to everyone here, is we can talk at a very high level about our HPC strategy at NSF. So specifically, I'll talk about the process and the motivation of why we're moving towards a leadership class computing facility. I can talk about the community that is providing input to us. NSF is, in its DNA, a very bottom-up organization, and so we often what we do in terms of programs are driven by what the community needs. And so I'll talk a little bit about how we've been gathering that piece of information to motivate many of our HPC programs. I'll also talk about our existing experience with Blue Waters, which is our current leadership class system deployed at the University of Illinois. And then finally, I'll talk about our roadmap. And specifically, I'll talk about the solicitation itself, our plans, our goals, why we think it's a good thing. All right, so just to put things in context, NSF funds cyber infrastructure, and cyber infrastructure really is a holistic environment. It's certainly computational resources are important because ultimately that's where the rubber hits the road. But we also fund things like infrastructure software. So certainly, a piece of hardware is never useful, like we all know, unless the software enables users to be productive on it. We also fund data. We know that the proliferation of data now in the scientific community and what drives many of our newer discoveries through the analysis of data. We fund people, certainly, because we know that it's people that make things work. So we fund things like SEED, for example, which is the organization of 19 institutions that provide the expertise for researchers to be productive on HPC systems. We provide the networking to enable collaborative work. We provide the plethora of scientific instruments throughout the agencies in our different directorates to enable scientists to be productive in the scientific endeavor. All right, so that's just to place things in context. So in terms of feedback that we've gotten from the community that has driven our policies and our roadmap. So we've been, I put up 4 specific inputs that we've gotten that has quite heavily influenced our thoughts about what the leadership computing facility should look like. So for example, a number of years ago, we commissioned the National Academies of Science to come up with a report to basically convene a committee to author a report that to advise the agency on what the future directions should be for the NSF advanced computing infrastructure within the time frame 2017, which we are now, to 2022. In addition, we also are driven by the National Strategic Computing Initiative. This was I think we all know, this is the initiative that was initiated by our previous administration. By all accounts, that initiative is still ongoing. We have not heard anything else from OSTP, so it's onward we go at NSF with regards to NSCI. We also have a biannual advisory committee called the Advisory Committee on Cyber Infrastructure. This is chaired by Tom Dunning out at the University of Washington and Gwen Jacobs from the University of Hawaii. They meet biannually, and they provide us with advice on our programs and give us thoughts from the community so that we can incorporate that in the things that we do within our office. And then finally, also, we have also been incorporating some ideas that we've gathered from the Dear Colleague letter that we issued that was issued earlier this year, but which closed in April 2017. That was a Dear Colleague letter requesting the community to provide us with their vision of what cyber infrastructure should look like moving forward to the year 2030. So I'll just quickly go through some of those community inputs that have driven our thoughts. So certainly the National Strategic Computing Initiative. As we all know, there were 5 objectives. NSF was given the leadership role in 3 of them. So they were to explore the technical synergy in modeling and data analytics. We were also tasked to look at beyond Moore's law, new devices, new architectures that will allow systems to scale beyond current limits. We were also asked to look at the ways of increasing capacity as well as capability within the national HPC ecosystem. And I think the third objectives in particular spurred on our motivation for thinking that we need a leadership class computing facility to serve the wider scientific community. So we also, as for the National Academy study, so specifically we asked the National Academies of Science to examine the anticipated priorities and the associated trade-offs for advanced computing for our agency in terms of supporting our science activities. And so the National Academies of Science convened a committee, and they appointed 2 co-chairs to solicit feedback that ultimately resulted in the report that was issued in the middle of 2016. The co-chairs were Robert Harrison and Bill Grob. Robert Harrison is from Stony Brook University out in New York, and Bill Grob is from the University of Illinois. And so very quickly, too, there were 7 recommendations, and so broadly, we've categorized those 7 recommendations into broad themes. So for example, there were recommendations pertaining to continued leadership in science and engineering. There was a set of recommendations that urges the agency to ensure that resources meet community needs. There was also another broad theme that basically is asking the agency to aid the scientific community in keeping up with the computing revolution, right? Because things are moving really fast, right? The architectures are changing, new systems are coming up, and so scientists are having a hard time in trying to keep on that leading edge. So that was the third theme. And the fourth theme was provide a more sustainable infrastructure for advanced computing. Because NSF typically provides 3-year grants, and for the larger infrastructure awards, it's been typically 5 years. And so that's certainly viewed as a very short time span or short horizon for supporting infrastructure that scientists can come to rely on. And so we're looking at strategies to kind of improve that sustainability model. So I've highlighted 2 of the actions or the responses that we've taken that kind of addresses directly our leadership class computing facility support. So one is, we've put up a solicitation. This was issued sometime in May of this year. And I'm going to be talking a lot more about that in the next couple of slides, but it's certainly something that we hope that will address the recommendation pertaining to keeping the nation at the leadership in science and innovation. Also, in the theme of sustaining infrastructure advanced computing, that's also an area in which the solicitation is attempting to address, because we are pursuing the use of an account and a process within the National Science Foundation called the Major Research Equipment and Facilities account. So that's the acronym is MREFC. Because typically the agency does support long-term infrastructure. We support many telescopes, for example. We support ships, exploratory ships. We support many things, right? Like LIGO, for example, is an observatory that has spanned many, many years. And so we're thinking that the facility itself would fit within this model. It will be a major research equipment, so to speak. Okay, very quickly from the Dear Colleague letter requesting feedback from the community concerning what cyber infrastructure should look like in the future for us. This is just a breakdown of the the fields from which the respondents came from. So you can see 31% of the respondents came from the general field of cyber infrastructure, but we certainly had good representation from all the different science directorates as well. So for example, math and physical science had approximately 21% of the had 25% of the share of the respondents. Life sciences were well represented too, geosciences, engineering, computer science, and education and learning. Although one thing I would say about education and learning is that education and learning was pervasive in all the respondents' answers to our request for what cyber infrastructure should look like. Education and learning issues are, I think, one of the number one themes that came up from this request. So anyways, this is a summary of some of the initial insights that we had. And I just wanted to highlight just one of them. And so certainly advanced computing is still an important issue, and certainly is an issue that requires NSF to provide some form of advanced computing infrastructure for the future of our national scientists and engineers. But one thing that we do note is that the modus operandi, or the style of usage of computing is evolving. So certainly I mean, still the batch style of using a supercomputer is still prevalent today. But certainly, things like computational steering is important. It's becoming more important. Things like rapid data processing, in fact, real-time data feedback processing in order to provide real-time feedback is also quite important, especially driven by experiments, which are creating a deluge of data. Also, the ability for simulations to work with huge amounts of data for comparison, for validation, and all of that, that's quite important too. And so certainly that will influence the types of infrastructure that we will deploy for our NSF-supported research activities. Now, before I go on to the next set of slides, which talks about Blue Waters, are there any questions? Okay, good. So I just wanted to quickly talk about our experience with deploying Blue Waters. So one of the things that we knew from the onset when we wanted to deploy Blue Waters is that we wanted to provide a capability beyond any other capabilities that were available at the time for our nation's scientists. And so certainly Blue Waters has been doing that. So I give you one of many examples really of the types of science that are relying on the capabilities of Blue Waters. So for example, this is from Tiziana Di Matteo from CMU. She's a cosmologist. She runs some of the largest cosmology simulations in the world. She looks at the earliest quasars, the formation of quasars. And so, for example, some of her runs on Blue Waters have typically spanned almost the entire machine. So there are 23,000 nodes on Blue Waters. So she's been using up to 20,000 nodes on Blue Waters. And much of her simulation involves, it's a hydrodynamic simulation, so she has many particles. And so she has, in her simulations, she simulates up to 1 trillion particles. And all of these particles are in memory while the simulation is running. And so consequently, her simulations are using the full memory capabilities of the system. That's 1.2 petabytes of memory. The other thing that also is equally important is the capacity that Blue Waters provides. So like I said, Blue Waters has 23,000 nodes available in the system. And so this is one example of the capacity that is providing new insights for us as a nation. So for example, Paul Moran is standing right behind you. He has been leading a team that's been using Blue Waters to basically run analysis to create a digital elevation map up to 2 meters for the entire Arctic. And so that's never been done before. It's providing new insights as to the state of what the Arctic is right now, and gives us an opportunity to see how the Arctic evolves over time. And his task, right, is really not a parallel task. He just simply has to run many, many serial jobs. And he has up to 1 million analysis he has to do. And he's been going to be doing that over 2 years. And he's churning through over 400 terabytes of data. And so that's a quote from Paul, right? Paul, you can correct me if that's inaccurate, but he says, Blue Waters has exceptional resources and one of the only HPC centers with the capacity to complete this project. So it's the capability and the capacity that Blue Waters is providing. And I think that's what we're thinking is going to be of continual importance to our program. I'd also like to talk a little bit about how the usage of the system has also evolved over time. So middle of last year, we asked the University of Buffalo to conduct a workload analysis, a study on the jobs that are running, on the science that have been performed on Blue Waters. And this really is a plug for their report. It's a report that's quite extensive, and it's very insightful. It's over 100 pages long, and I've just extracted a couple of things that I think are important. So if this is of interest to you, I would urge you to go to the link that I have there. I've provided these slides to the HPC User Forum, so it will be available to anyone after this talk. So anyway, the report is available, but I just wanted to highlight the increased diversity of usage on Blue Waters. So on the top left-hand chart, right, the one with the orange bars, you'll see that represents the fields of science that have been using Blue Waters. And so if you look at 2013, we had approximately about maybe 25 fields of science that were represented by the teams that were using Blue Waters. But by 2016, you see that we have over 60 different fields of science that are being represented on Blue Waters. So there's a growing diversity of usage from the various directorates activities that we support across all of science in our nation. For the bottom right-hand, I guess, right-hand for you, graph, you'll see the representation in terms of the different directorates that are funding these activities. So the blue line, the blue bar is the Math and Physical Sciences Directorate. And you see it's dominant early on in the lifetime of Blue Waters. So 2014, for example, you see that huge spike. See if this laser works. Oh. You see MPS, the Math and Physical Sciences, were the dominant users on the system. But you see over the years, in 2016, for example, the other directorate sciences are using the machine as well. So, for example, the red bar is biological sciences. The orange bar is engineering, and the kind of the gray and green, dirty green bar, I guess, it's the geosciences community. So you see a more even mix of different scientific activities on Blue Waters. Yes?
Quick question. In the previous slide, you had cybersecurity as one, the largest group for the next one. Is there cybersecurity research happening now on Blue Waters, or is that?
Not a lot. Not a lot.
Big shift because of what's been happening.
That's true, but I think cybersecurity will fit within the SISE directorate, which is the Computer Information Systems and Engineering. There's been typically far fewer SISE teams using the system, because the system is primarily viewed as a specialized physical sciences experimental instrument, right? And so we have other test beds which serve the SISE community. For example, at the University of Texas, there's a cloud system called Chameleon, which allows cybersecurity type research to be performed on that. And so many of our SISE researchers will go to those types of test beds, because those are extremely reconfigurable. And so I think that's what computer scientists want. Yeah. So the other thing that we're seeing too is that the job sizes are also kind of, the ratio of large jobs to small jobs is also kind of equalizing over time. So for example, I just want you to focus on the yellow, I guess, the yellow line. So the yellow line is really the bucket that represents all jobs. There are over 2,000 nodes. And what you'll see is that, over time it's kind of becoming less prominent compared to the others. So for example, the blue line are jobs that are asking from 1 to 64 nodes only. And so over time, over the years, what we're seeing is that the job size the ratio of the large jobs to small jobs are kind of converging. And I think the reason why, we're not completely certain what the reason for this is, but the hypothesis is that it's due to the diversity of usage. So we see, like, for example, from fields of sciences like chemistry and molecular biosciences, where typically their large jobs are, in a 64 to 128 node range, and so since we're seeing a lot more researchers from those types of communities coming onto the system, what we're then seeing too is that the rise in these smaller type jobs on Blue Waters. And so also what we're also seeing is that, that typically, so just a little background. So Blue Waters is deployed and it's run by the University of Illinois, but the allocations on the system is actually run by NSF. So 80% of the system is allocated through a peer review process. We have a solicitation out on the street every year. It's called the Petascale Compute Resource Solicitation. And so scientists will write a 15-page NSF proposal, and we review it for intellectual merit as well as broader impacts before we actually recommend an allocation on blue waters for the teams that are requesting it. And so typically what we're seeing is that the numbers that have been recommended through our peer review process compared to what we're able to actually allocate out has been approximately about 3 times oversubscribed. So we're seeing that consistently throughout the years in which we've been operating blue waters. So any questions before I move on to the next set of slides talking about our future? So that was basically our present. And so I'm just going to talk a little bit more about our future. Okay, I only have maybe about 5 or 10 minutes, so I'll just quickly go through the roadmap that we've come up with. So again, we at NSF, we don't support one system, we don't support 2 systems. We support a community or a set of distributed resources. And these distributed resources addresses different things that have been seen as important in the wider, broader computational science community. So for example, Blue Waters is our leadership system, and that provides the leadership capabilities and capacity that's needed, right? And so that system is going to cease operation in March 2019. We've been in planning since early 2016 on what the follow-up should be, which has resulted in the solicitation that's on the street right now. And the ultimate goal is that we hope that the solicitation will enable a new system to be deployed sometime in 2019, where it will provide from 2 to 3 times capability improvement to the current Blue Waters. But ultimately, we want this to be a sustained infrastructure for leadership computing. And so we presume that this will be ultimately a 10 to 20-year activity. And in the time frame somewhere around 2003, 2004, we expect that the initial phase 1 system is going to be upgraded to a system that's approximately about at least 20x that of what current Blue Waters provides. So that's our leadership computing sphere. We also provide to the broader HPC community, the computational science community, systems at TAC, for example. We've recently deployed Stampede 2, which is an 18 petaflop system that's going to be fully in operation sometime in the fall of this year. For the atmospheric community, supported through NCAR, they have recently deployed Cheyenne earlier this year, and that's, I think, a 6 to 7 petaflop system. An SGI system. Comet, which is deployed at the University of California, San Diego at SDSC. There is a system that basically supports the long tail of science, so these are moderate-sized jobs. Bridges is, and I know Nick Nystrom is here. Bridges is a memory-intensive system that's meant to support jobs that require lots of memory, as well as desktop computing. And Jetstream, which is a cloud computing resource. But we have plans for future systems that will replace these systems that will ultimately cease operations. Okay, so very quickly, so consequently, with all that said, right, we think that we need a leadership facility. We came up with a solicitation out in this past May. We asked for a letter of intent so that we know who's going to be submitting proposals. So that was this past July. November is when we get the full proposal. We'll be evaluating it, and sometime early next year we'll decide an awardee, and then we'll have a project plan, right? But the high-level goal, right? So I'll just quickly go through this since I only have about a minute. Is that the goal of this phase 1 system, which is going to be a $60 million system, we hope that this is going to be a forward-looking computational asset, right? That's going to be 2 to 3 times capability improvement over Blue Waters. But in addition to that, we also wish that this system is going to be an evaluative platform for the future system, which is going to be at least, like I said, 20x that of current Blue Waters. And so this is the timeline we're expecting from the awardee. So the blue line, so the top blue line shows where Blue Waters will cease operation in March 2019. The bottom blue line shows our expectation for awarding a full-on system and then a 5-year operations for that phase 1 system. The red line shows the planning phase. So in addition to operating this phase 1 system, we're expecting the team to engage in the planning and design for the upgrade, right? And the upgrade is going to be potentially a facility too. It could be a building that needs to house this future system. And so consequently, that red line demonstrates that parallel activity that will be happening with this eventual awardee that we don't know yet, right? So with that, thank you. And if there are any questions at all, I'm happy to answer. Yes?
So the topic of cybersecurity was brought up a minute ago with regard to the work that's being done on the Blue Water Mountain facility. I'm kind of curious, what work is NSF doing to look at the cybersecurity of these high-performance computing facilities and resources to ensure that they can operate if they become, say, the target of malicious activity?
So I can speak about the operational aspect because, for example, one of the things that we ask from proposers when they put forward a proposal to acquire a system to serve the NSF research community is what the security plan is. And this involves not only cybersecurity, it involves also the actual physical security of the facility that will be hosting or deploying the system. So we evaluate every proposal that comes in, and that's one of the evaluation criteria we look at. In terms of cybersecurity itself, I can talk in terms of the interagency interest in that. So for example, in the purview of NSCI and NIST, the National Institute of Science Standards and Technology, they've been hosting a series of HPC security workshops that many agencies are participating in. And so the different agencies, including NSF, are sharing their experience in operating these types of systems and what the concerns are, the evolving needs are, and potentially what the research issues are so that we can engage the community to kind of solve those problems. Yeah. Any other questions? Yes?
If you go back to your previous chart, I think it was, where you had
which one?
The timeline one.
Yeah.
Just so I understand, so for phase 1, you're looking 2 to 3x actual delivered performance improvement. And then the previous chart, you said 20x for kind of phase 2.
Yeah.
Do you plan to spend a lot more in phase 2 than phase 1, or do you think the technology will keep?
Oh yeah, we expect to spend a lot more.
In phase 2?
Yes, that's right.
The ratio there,
yeah. Yeah, and that's where the planning phase actually comes in. So the planning phase will come up with a cost estimate, and that cost estimate needs to be verified and validated. So yeah, and so there's a process within NSF where we do that, and so that will then result in the request to Congress for funding for this next phase, and then if everything goes well, we'll get that funding, and that will fund the phase 2.
Great,
all right. Any other questions? Yeah.
So do you have a non-recoverable engineering phase as well? I mean, do you plan to fund vendors to build specific technologies?
We don't have the equivalent for what DOE has. We do have research programs that look at future programming environments. So for example, in SCIES, which is the Computer Science Directorate, it has the Scalable Parallel to the Extreme program where we have teams that are proposing new environments that addresses the entire stack, so from the programming paradigm down to the hardware level, and they include application scientists as well. And so we do have that, but that's so typically NSF funds things through the academic community. So many of these academic proposals or projects have industry partners, they have vendor participation, and that's how vendors participate through those types of programs. Yeah. Any other questions?
Great,
Thank you very much.